Hey everyone, Mr. Boltri here, bringing you video 1.3 of AP Physics. Today we're going to be talking about what the different graphs of motion, one-dimensional motion, look like. So today I'm going to cover four major topics. The first is just a different way to represent motion called motion maps. Then we're going to look at the position time, velocity time, and acceleration time for circumstances in which there's constant acceleration. We're going to look at the relationship between positive acceleration and speeding up, see if those always mean the same thing. Spoiler alert, they do not. And then we're going to look at the xt, vt, and at graph for a situation in which the acceleration is not constant, which is where things get really fun and interesting. So first, this isn't really a graph, it's called a motion map. It's a different way to represent motion that AP will throw in sometimes. So you need to be familiar with how to interpret what you're looking at, but it is pretty straightforward, pretty intuitive. So the biggest thing is we're looking, this is called a stroboscopic view. And if you've ever been to like a party with like a strobe light, that's kind of what you're looking at. Is like basically imagine if you were to close your eyes and all you'd be able to do is open them for like just a flash every 1 second. You would see a jogger here, and then you'd close your eyes and you wouldn't see anything for another second. And then you open your eyes, now the jogger's here. Now the jogger's here. Now the jogger's here. And you wouldn't see anything happening in between, just like blop, blop, blop. So this is just a bunch of different positions at a bunch of different times. At time 0, the position is 1. At time 1, the position is 5. And then on from there. So some questions that they might ask based on this is which of the runners, the jogger or the sprinter, has a greater acceleration? And that would just ask you to recognize that here the velocity seems to be pretty constant because every second they are moving a set amount. And then here there is some noticeable acceleration because every second they seem to be moving a greater distance, which is indicative of some sort of acceleration. And actually you can see that using our more familiar friend, the position versus time graph. They could ask other questions like when are they in the same position at the same time? And so it might be sometime between 1 second and 2 seconds, and then again kind of around 3 seconds. Those would be the 2 times that they would be in the same position at the same time. They could ask when do they have the same instantaneous velocity? And so then you'd have to look at the slope of the green line and the tangent slope of this red curve. And it looks like it's somewhere around the 2 second mark. The tangent slope would be parallel to the average velocity of the jogger. So that's just a different way that they might show you motion, and you need to be familiar with. So now let's go back to the familiar xt, vt, and at graphs. And I just pulled this document from something that I made for my freshmen. So wherever it says P for position, we know we have to use X because P stands for momentum. So this is xt, vt, and at graphs. So I just kind of wanted to take you through what some of the more basic graphs would look like so that we can have a really good foundation going into some of the more advanced graphs. So if something's not moving, the velocity is 0, the velocity is not changing, so the acceleration is 0, and the position just stays the same the whole time. It's real simple. Something moving with a constant velocity, we've been over this, is a linear PT graph with a constant velocity, and the velocity is not changing, so the acceleration is 0. So that's all pretty straightforward. Here's where things get to be slightly more interesting. This is interesting on the freshman level, and for you guys, I hope you're crushing it at this point. But one of the things that AP really likes to do is they really like to start you off with the velocity versus time graph. And because then they can ask you to go up here and think about the position versus time graph, or they can ask you to go down here and think about the acceleration versus time graph. So they love to start with the velocity versus time graph. And I just kind of wanted to start to get you a sense of what the different position versus time graphs looks like associated with different velocity versus time graphs. So the biggest thing here is just recognizing that if the velocity value is positive, that means the object is moving in the positive direction. Doesn't matter if it is has positive acceleration or negative acceleration. A positive velocity means it's moving in the positive direction, period. Negative velocity means the object is moving in the negative direction. Doesn't matter if it's speeding up or slowing down. Negative velocity means the object is moving in the negative direction. So you can see here the slope of the xt graph is very shallow at the beginning, which corresponds to a very small velocity. And then the slope gets bigger and bigger, which corresponds to a bigger and bigger velocity. And then the opposite is true here. Steep slope at the beginning, which is a big velocity at the beginning. Shallow slope approaching zero slope at the end as the velocity approaches zero. And you can do that. That's one really easy way to translate back and forth between position versus time and velocity versus time, is to look at the slope of the position versus time if you're given the position versus time, or know that the velocity versus time tells you the slope. So this tells me, okay, at the beginning it has a slope of zero, then the slope is a small negative number getting bigger and bigger, zero slope, small negative slope, big negative slope. And that's just the way that you can translate back and forth between those to recognize what kind of motion we're looking at. Which direction we're moving in, are we speeding up, are we slowing down? And then obviously the accelerations on all of these are constant because we have a bunch of linear VT graphs, but we can figure out the acceleration by looking at the slope of the VT graph. If the slope is positive, we have a positive acceleration. If the slope is negative, we have a negative acceleration. So that's kind of how you can get used to quickly and easily moving back and forth between these different representations of motion. So I just wanted to do this one specific example, just because on the AP exam, they might give you a velocity versus time graph and say, which of these position versus time graphs match the velocity versus time graph? So just by looking at this, I know that because the velocity values are all in the negative region, the object is going to be moving in the negative direction. I think it's going to be moving the negative direction pretty fast at first, and then slowing down, slowing down, slowing down. The slowest velocity you can be going is 0 meters per second. So it's getting closer and closer to the slowest it can be going. So what this is going to look like on our position versus time graph is a steep negative velocity at the beginning and slowing down, getting more and more shallow until eventually it's just kind of stationary. So that is the one possible position versus time graph. But you'll notice that there's nowhere in this velocity versus time graph, unless the problem tells you specifically, that says anything about the initial position. We can find the area, which would tell us the change in position, but there's no information on the velocity versus time graph about where the object started. So I kind of arbitrarily chose the origin because that's usually a pretty easy place to start. But the object could have also started way up here, in which case the motion would look pretty much identical, but starting from a different starting location. So that's the kind of question that they might ask. They might say, which of these is possible given this velocity versus time graph, in which case either of these two position versus time graphs would be a possible match for this velocity versus time graph, since the velocity versus time graph does not have any information about starting position. In the same way, an acceleration versus time graph doesn't have any information about starting velocity. All this tells us is that the velocity is getting more and more positive. So if the velocity starts at 0 meters per second, then it gets more and more positive. This is the object speeding up because it's getting farther away from the slowest velocity possible, 0, at speeding up. But if the object had an initial velocity in the negative region, then it would actually be getting closer and closer to the slowest velocity possible, 0. So I show you this to dispel the notion that positive acceleration means speeding up. It does not. That's not true. Positive acceleration sometimes causes objects to speed up if they had a positive velocity to begin with, or if they had a negative velocity to begin with, the positive acceleration causes the object to slow down. So Definitely, I want you to remove positive acceleration equals speeding up from your brain, as well as make sure to remove the word deceleration from your brain. Physicists don't really talk about deceleration. We talk about positive acceleration and negative acceleration. And if you want to say something is speeding up, go ahead and say it's speeding up. If you want to say it's slowing down, say it's slowing down. Don't use deceleration to say something's slowing down, because deceleration, to me and to some AP graders, might make them think you're thinking about negative acceleration, which just like positive acceleration does not always mean speeding up or slowing down. So remove deceleration from your vocabulary and just use speeding up and slowing down instead to say what you want to say, at least as far as when you're taking the AP Physics exam is concerned. So positive acceleration, we know, does not necessarily mean speeding up. It could in some circumstances, and it doesn't in other circumstances, but it definitely means that the velocity versus time graph has a positive slope. That's just that is just the definition of acceleration. Positive acceleration means positive slope on the VT graph. So what does this look like on the position versus time graph? Well, it's going to be moving in the negative direction, slowing down, and then moving in the positive direction, speeding up. It's going to look something a little bit like this. So this graph shape is, I'm going to introduce a new vocabulary term for you, which is called concavity. This graph shape is what we call concave up, because it looks like a cup. Concave up, like a cup. And what all that means is that the velocity is increasing always due to the positive acceleration. So you can remember this because positive acceleration, positive people tend to smile more. So if you have a positive acceleration, it's going to be true that your velocity is going to be increasing, whether that means getting closer to zero in the negatives or more and more positive in the positive. But you're going to get a graph shape that looks like this big smiley face, which is concave up. And then conversely, negative acceleration is going to give us a concave down. So this is going to be moving in the positive direction, but slowing down, and then moving in the negative direction, but speeding up. We're going to get something like this, which again makes sense because negative people tend to frown more. So concave up like a cup, it's a happy face because of the positive acceleration. Concave down like a frown, it's a sad face because of the negative acceleration. And this all goes back to what's going on with the acceleration, because it's negative, causing the velocity to look like this, which is causing the position versus time graph to look like the sad face, just like that. So that's an easy way to be able to look at the position versus time graph and know, just by looking at it, whether the acceleration is positive or negative based on the concavity. If it's concave up, positive acceleration. If it's concave down, negative acceleration. And just, you guys know, I really love graphs. I love looking at things in graphs, but I know different people like seeing things in different ways. So this is a table that's showing basically the same thing that I've just been talking about. Of if the acceleration is the same sign as the velocity, that means it's speeding up. If the so negative, speeding up, positive, speeding up. But it's when they're working against each other, like you have a positive velocity and your velocity is getting more and more negative, or vice versa. You have a negative velocity and your velocities are getting more and more positive acceleration. That's what's going to cause you to be slowing down. So this I just show you to show that positive acceleration does not always mean speeding up. Negative acceleration does not always mean slowing down. It depends on the signs and how those two things are working together. Okay, so last but not least, those have all been examples with constant acceleration. And the concavity rules still apply. And all the general rules still apply. Things just get a little bit more interesting when we have a changing acceleration. So first, let's just look at the most basic example of a constant velocity. When we have this linear position versus time graph, we know the slope of the linear position versus time graph is the velocity. Linear slope turns into a constant velocity. Then the slope of the constant velocity graph gives us 0 because the velocity is not changing. The slope of this is 0. The acceleration is 0. So our linear xt graph turns into a constant, vt graph turns into a 0 AT graph. Let's look at what happens when we have a non-zero but still constant acceleration. Our linear or our constant acceleration gives us linear change in our velocity versus time graph, which then ends up giving us some sort of quadratic shape in our position versus time xt graph. So now this is the most fun thing, is when we have a linear acceleration versus time graph. That means that as time is increasing, the acceleration is getting bigger and bigger, or smaller and smaller. But in this situation, let's just say the acceleration is increasing with respect to time. So what do we think that the velocity versus time graph might look like? Very much like over here, where we have, okay, well, the velocity is small at the beginning, and then it gets bigger and bigger. That means the slope here is small at the beginning and then gets bigger and bigger. Well, the same thing is going to happen with the acceleration versus time in relation to the velocity versus time. That means that at the beginning, the velocity is not changing very much. But then at the end, the velocity, the change in the velocity gets bigger and bigger. So we actually end up with a quadratic velocity versus time graph, where we see small changes at the beginning, small tangent slopes, getting to be bigger and bigger tangent slopes corresponding with the bigger accelerations. So then the question that I'm going to leave you today is, if we have a quadratic velocity versus time graph, what do you think the position versus time graph is going to look like? And I'm hoping you get that right, because we are fully into calculus now. I'm not going to go into as much depth as Mr. Taylor and Ms. Harper are going to, or your calculus teacher, but I'm really excited to do a video on recognizing the patterns in the way that the graphs work with each other, tying that calculus into physics. But that's going to be for a future video. This video, the purpose was just to take you through the different kind of graphs that you're going to be seeing on the AP exam, and kind of start to allow you to understand how to translate between one graph and another graph. So this is Mr. Boltri wrapping up video 1.3, where we've covered kinematic graphs. Go Bears.